I'm going to present another solution to the traveling salesman problem. This category of algorithm is called branch and bound. So we're going to just quickly review the traveling salesman for a second. So we want in the traveling salesman, each node in the graph or each vertex is a city, and the edges are the costs to move between the cities. We want to start in a city, visit all the others, and then return back to where we started. And we want to do this having visited each place exactly once, and find the cheapest way of doing this. So that's the traveling salesman. Just also going to quickly apologize for my learning a new LaTeX skill set here, so my graph is a little janky here. This 7 is the cost from going from B to E, and this 9 is the cost from going from D to C. But yeah, LaTeX fun. Always learning something new. Anyways, let's review a few solutions to the traveling salesman. So I've covered a greedy approach. That's two-opt. That starts with a tour and then performs a bunch of swaps and tries to find a better answer. This is fast. It's approximate, and it's pretty simple. So it's a lot of pluses for it. Then there's a dynamic programming solution, the held carp algorithm. It's pretty slow. It's an exponential time. It takes a lot of memory to get there. The cut from factorial amount of time down to exponential does that via using a lot of memory. However, it will give you the optimal solution. After that, I've covered a randomized approach, a genetic algorithm. So it's fast, it's approximate. It'll typically should give you a better answer than two-opt. The downside is there's a lot of tuning necessary. So there's a lot of additional sort of parameters you just got to tweak and sort of optimize for, and that's really essential for getting good answers out of that. So it's got a little bit of black magic associated with it, but it's pretty powerful. So last time I covered the like a backtracking algorithm for the n queens problem. So can we use backtracking for optimization? Well, since you're watching this video, of course the answer is yes. It's called branch and bound. So the high level steps here is we're going to use, if you remember, backtracking essentially just depth first search. We're going to look for any old solution with depth first search. Once we have that solution found, we know its path length or its distance or its cost, whatever you want to call it. Now when we go to start looking for additional solutions, we can judge the sort of partial tours and look at their distance. If they're already cost more than the solution we found, we don't need to consider, how do we finish this partial tour. That's just a dead end, so to speak, in terms of search. So we can just throw it out. That's the bounding or sort of pruning operation. And then so long as a partial tour looks viable, that is, it's less in cost or distance than the solution we found, we'll keep pursuing it until we find the complete tour. And if it's better than what we found so far, then we'll update and continue. So it's sort of big picture of this. I'm going to use this example graph I started with. Because of sort of screen real estate, you might want to just pause and write this down real quick, though it's not critical that you know all these numbers as I go through the example. But if you want to, you might, write it down or screenshot it or open up, the same video again and have two copies and just pause one here or something crazy like that. Anyways, that's the real lazy solution. Yeah, so keep that in mind. This is an example graph I'm going to use. So there's 5 vertices. A is going to be the depot. The best solution is going to be going around the outside. Also keep in mind it's undirected. So we're going to talk about the state space or the search tree. It's going to be a list of the vertices. So that's going to correspond to a path. and then hopefully to a tour. All we're going to do is, given a partial tour, we're going to take all the vertices that are not in it and then add those one at a time to generate new tours from it. So that will give us this sort of tree structure. So since there's A, B, C, D, E in the graph, we'll exclude A and then add B, add C, add D, add E. So we'll generate more partial tours based upon a given tour. So that's also our notion of a successor function. So given a state, we can generate more states. Excuse me. And we can judge too pretty simply when we're done, once we include all the vertices, and then we'll have to make a special trip from wherever we end up back to the beginning. So that'll be sort of one special case in our successor function that I haven't like visually laid out. That's just a detail. Now let's walk through an example. So this is going to generate a very large graph, but we'll see. I can't reasonably put it all on the screen at once, so we'll walk down different branches of it. So we're starting with A. So since that's our depot, our initial state is a tour. It's an A. So we're going to add in the vertices alphabetically. So we'll add in B is the next thing that's not in our current tour, which only includes A. So we'll add in B. So that's this slide is just showing that part of the tree. And since this is depth first search, we're going to continue down this utmost left side. Also, I put colon the cost or the total distance of the tour over here. So you can refer to the graph and sort of verify that hopefully I haven't made any mistakes. But also, you probably don't really need to actually look at the graph to sort of follow along if you just sort of believe these numbers as they appear. Anyhow, so we have AB. Okay, now we're going to add the next vertex alphabetically. It's not included, so that's C, A, B, C, D, A, B, C, D, E. And then finally, since this is the last two steps are basically deterministic, or rather, not just deterministic. There's only one possible place to go. So we can only go to E, and from E, then we return back to A to make it a tour. So I've colored green solutions. So this is a complete solution. It costs 22. That's not going to be relevant, but we'll file that away. So now the best one we found costs 22. That's actually not great. So now we're going to backtrack. We're going to backtrack up to the last real decision point. These last two, there was no other alternatives. So we backtrack up to here. Now instead of adding D next, we'll add E. So this is under 22. We'll add in D. This is under 22. We'll add in A. This is, again, under 22. So now this is our best. So now 14 is the best tour length we found. So now we're going to backtrack again up to AB. So we've removed C. Now we're at ABD. Right, so that's the next one alphabetically, if you're seeing that. Now add in C. Now CE. So we're still under 14. So this hasn't helped us at all in terms of pruning. We haven't done any of that. So far this is just exhaustive with depth first. And now we've hit ABCEA. So this is 20. We've now evaluated this. It's not better than this previous solution. So we're just going to remember this, 14. We'll backtrack up to here. Again, we'll fill it out. Now we get to finally a useful solution at 10. So now when we backtrack up to B, or to AB rather, when we look at ABE, since that's the next one in this sort of level, its total cost, if you add up A to B, then B to E, is 10. Now, since that is tied, remember partial solutions must be under the best thing we've found so far, because we know we need to add more to this to finish it. So whatever the actual cost of any possible solution is going to be 10 plus something, And since that something isn't going to be negative, we know we don't need to pursue anything following Abe here. Sorry, Abe. Now we'll backtrack all the way back up to A. So this is our first instance of bounding, if you will, or pruning. Branch and prune sounds like a brand for like raisins or something, or some kind of weird fruit brand, or maybe some hippie brand or something. Anyways, I think they picked branch and bound from alliteration, but I think pruning is a better word than bounding. Anyhow, so we're going to backtrack to A, and then I'll move to the next slide, and we'll consider a different branch of this tree. So it's already looking a bit more sparse. You can see there's some much more pruning happening here. So we'll take A. Now, the previous slide was AB was the prefix for that, essentially. Now we're on AC. Okay, we're under 10. We're throwing D, or B rather. We're under 10. Now we throw in D. Under 10. Oh, we get here. So we're one step away from the end, but there's no point to finishing. So we backtrack to the last real decision point up here. Now, when we put E on the end, it's up to 16. We can go ahead and prune that. Okay, now we backtrack to the last real decision point there. Add in D. Okay, that's tied with the best, so we just prune that as well. Because, again, we'll have to add more to complete this partial tour. So now we're down at ACE. Throwing B on the end, hits 10 again, so that's pruned. Okay, we can add D, add B, we're under 10. Oh, no, wait, add A. Oh, we've made it back. So if you look at the original graph, this is that good tour we found before, but this one's going in reverse. And since it's undirected, it's going to be the same cost. So that concludes the AC portion of the tree. So it's just going to get sparser and sparser. So now we have, again, 10 is the limit. So now we're doing the AD prefix. We'll add in B, add in C. Okay, now we've hit 11. That gets pruned. We backtrack up. Now we add in ADC. Okay, this is also going to get pruned. Now we explore ADE. Off of this, we have ADEB. Again, this is going to be pruned as well. Down to here, ADEC. So this is looking viable up to this point. We hit 13, and then, okay, this whole branch is dead. We backtrack all the way up to A. Now, once we hit the AE prefix, so if you look at the original graph, going from A to E is the most expensive edge. So it makes sense that, well, nothing looks viable off of it. So we try growing the tour in 3 different ways we can. None of them are useful, so they all get pruned. Cool. So can we do better than this? There's this idea called a heuristic. That's a rule of thumb. It's, outside of computer science, like a heuristic, you might consider like the phrase, you get what you pay for. It's sort of a rule that generally works, but it's not considered maybe 100% true, but it's kind of good enough. So we're going to use this idea of, well, when we evaluate a partial solution like A, B, D, C, we need to add in E and A, right? So it's a partial solution. We can measure how much the partial solutions cost, like what its path length is, but we know there's going to be some extra cost associated with adding in E and A. So a heuristic is just sort of like a decent guess at what that would be. And the key here is you want to be, there's this quality called admissible or admissibility. You never want to overestimate the remaining cost. If you overestimate, then you end up pruning too aggressively. So if you said, oh, the remaining cost to add this in is going to be 10, but it's actually 5, you could be missing the optimal solution because you said it was going to be higher than it actually was. So you don't want to go too high, but you don't. It's better to. that estimates something other than just 0. So then we can prune a little more aggressively. So one very, very simple heuristic is to take the cheapest edge in the graph, which is 1 in this case, and then just count the number of edges you need to finish the tour. So I'll go through this example again. It's going to be, much, much, much faster now. So with that, I can show you the whole tree because it gets pruned a lot more aggressively. So starting at A, we're going to do depth first style down this left side. Now what I have here is the actual cost from A to B is 1, but since I need to add in 4 more edges, and we know the minimum cost of an edge is 1, so I can just safely add 4 to it. That's never going to overestimate. That's just the cheapest possible way to get there, even though that's actually not possible at all. But we can see even with just something this simple, so this first bit of the tree is the same. So we end up visiting here for 22, 14, 20. Now when I get down to here, I can find 10. So now we know when I eventually want to come up here and visit Abe again, okay, this one gets pruned. So really this whole tree over here, the whole AB prefix is the same. So that's not great, but when we backtrack, then go down to AC, well, now we can prune very aggressively here. So the original cost here was 7, but we know we need at least 3 more vertices, so 3 more edges at a cost of 1. Together that's 10, so that's not below the best we've seen so far. So that everything under this is pruned. Now, we add in, go back up here, so notice the heuristic cost up here is 4. Now we go to ACD, again, that gets pruned. Come down here, this gets pruned, and pruned again. So if you notice, this way led to an equivalent solution that was also 10, but we know at this point, even adding in 1 back, which it is, it won't work. Or it's not going to beat what we already have. So we're even able to prune there. Now when you come over to AD, all these are pruned out before, and then when we hit AE, well, there's no reason to consider anything that has that edge A to E because it's so expensive and it takes we have at least 4 more to include. So we've radically cut down the search tree here with the use of a very simple heuristic. So of course there's a lot of sort of art, I guess, to coming up with a good heuristic, and usually these are sort of empirically discovered, and it's really dependent upon the particular problem. So let's look at the stats. So the exhaustive tree should be 64 vertices, interior and terminal nodes as well. The first branch and bound, which I walked through, is 39 that we considered, assuming I counted correctly. And branch and bound plus a heuristic, we only considered 25. So you can see this makes a big difference. Again, the heuristic, this could help even more. It just depends upon, if you're clever enough, but you don't want to spend too much time because you're going to evaluate the heuristic on every vertex. That is like search vertex you find. Or every partial solution, rather. That's a clearer way to say it. Here's the pseudocode for it. So I'll walk you through this. This is very reminiscent of the pseudocode I showed you for the n queens problem. It's got that depth first search structure with some additions. I'm going to start with an empty stack here. That's what makes it depth first. We're going to have nothing as the best solution we found. We'll push in our initial, again, it's just a list with just the depot. And we're going to keep around a minimum cost. So that's going to be the cost of the best solution. So it's going to be infinity to start with because we haven't found anything. There's just this one main while loop. So while we still have candidate solutions, partial solutions to consider, we'll pop the top one off. If its path length is plus, so the path length, so that's its cost, distance, plus the heuristic. If it's less than the minimum, we'll continue. If not, it gets thrown away. All right, now if that's true, if where we are is less than the minimum and it's complete, so if it's complete, that must mean it's a better solution than what we found. So we'll update both accordingly. Else, this might be a little bit confusing. I'm looking at, well, if the size of the number of vertices in the tour is less than the number of vertices in the graph, we're just going to keep adding in vertices. So we'll go through each other vertex in the graph that's not in current. We'll append it to our current solution and push it on the stack. This is going to be I'm kind of assuming the data structure here is immutable, so that's maybe one thing to consider. There's a few different ways of implementing this. You could do it recursively. It's usually not a great idea because the depth of your stack can be really large. So I'm sort of assuming current something immutable, like it's like a linked list, immutable linked list or something like that, where we can just append to it, or depending how you set it up, prepend. But we're just going to add in the next vertex, and we're not going to alter the original version of current. We're just generating a new tour with this new vertex, and we'll do that for each that's not in current. So that's a branching step. And then this is so if this condition is false, that means we've added all the vertices in the graph to the tour. We just need the route back home. So I'm going to append current, or not current, append the depot to current. And that's basically adding in A in my example, so we actually complete the tour. And that's it. I think for what it does, it's relatively simple. Again, there's a few different ways of presenting this algorithm. My goal at least is to give you the one that's most easily understood or most straightforward to understand. But yeah, let's talk about how it works. So final sort of comments on analysis. The big thing is the runtime, right? How long does it take to run? We know held carp is n squared 2 to the n. Well, that's maybe the downside of this method. We don't really know the runtime. So, because the runtime depends upon the order in which you encounter your solutions, right? So if you happen to be, on that initial depth first dive, say right down to a solution, let's say you just get lucky and you get the answer. Well, now you're going to be able to prune, if you get the optimal route. Well, now you can prune really aggressively, right? So that's going to help a lot. Worst case is every time we discover a solution, it's the next worst one. So it's like somehow that your order of discovery is from worst to best. So then you're not pruning at all. You're not exhaustive. But given the whole space for this problem is, n factorial, the odds of that happening is very, very small. So that's almost like the worst case is just very unrealistic. So the kind of worst case analysis we've been doing doesn't make a lot of sense when applied to this sort of algorithm. Also, the quality of your heuristic can matter a lot too. It's hard to determine how much, but if it's depending on the setting, like if you're on a sort of Euclidean graph, it can help a whole lot. For example, so that's all, and it also makes a big difference in the runtime. So if you can sort of prune off in that sort of tree of your search, the higher up you can prune, well, you're cutting off large portions of the search tree. So a good heuristic can clip a few things early. That's going to make a massive difference in the runtime. You're not going to really get away from sort of working with this problem, having tinkered with it, and trying my own heuristics and implementations. You can't really get away from the fact it's basically going to be about exponential in time. You just hit a wall at some point. Problem still grows too fast. but it is more sort of memory efficient. I think is in practice faster than held carp. Of course, depending upon how you implement it, but that's sort of what we're sort of giving up on is good analysis. And the whole admissible heuristic thing, you know, there's a little more art we can throw in. We can throw in a little more, you know, if you come with good intuition about how to structure this for the problem, you have a real advantage over something like held carp or other techniques. So that's a real plus. Now, how does this relate to something else? There's another search algorithm called A-star. It's basically this, but if you replace the stack with a priority queue, so you go from depth first to best first, now you have the A-star algorithm. So A-star is thought of as generalization on Dijkstra's, which is essentially best first search. So this is really akin to it. Again, and then there's this trade-off again between best first versus depth first. So A-star versus just this kind of branch and bound with plus heuristic. Depth first can have an advantage in that, you know, adding or removing, pushing and popping to that stack is going to be faster, right? Also, we're going to get, the real advantage though is we're going to get to a complete solution faster. By faster, I mean we're going to explore fewer sort of interior nodes of that search tree before we hit a complete tour. And once we've done that, we can use that to prune aggressively. Whereas best first is going to, because it's prioritizing the cheapest thing first, it means you're going to look at a lot more partial solutions before you get to a full solution. So but again, it's like how long, what's that trade-off exactly? You just have to sort of measure it empirically. It maybe depends more upon the particular problem you're applying branch and bound versus A-star to. And again, these are very similar approaches. You change your data structure and now you're in A-star, right? So, yeah, so there's it's kind of fun coming up with different heuristics. I like this approach because it's really simple. It gets pretty good results. Plus, you get to have the sort of the fun of trying out different heuristics, seeing if you can sort of come up with something, give it your approach an extra edge. And then there's this whole quality layout, best first versus depth first. There's a lot of aspects, and just the analysis in general is sort of hard to determine, but its simplicity is pretty nice. So yeah, that's branch and bound for the traveling salesman.